This video will finish up Chapter 4. Motifs, also known as folds, are specific arrangements of secondary structure elements, and they can be composed of all alpha helices, all beta sheets, or a combination of both. Motifs are found as recurring structures in numerous proteins, and globular proteins are composed of different motifs folded together. Here are two common motifs, the beta-alpha-beta loop and the beta barrel. Here we have two beta strands connected with a helix. Here we have the beta barrel, which is a beta sheet composed of tandem repeats that twist and coil to form a closed structure that looks like a barrel. Oftentimes in beta barrels, the beta strands are arranged in an anti-parallel fashion, which is what's shown here. So this is going in this direction, and this is going in the opposite direction. The second term for describing structural patterns is domain. A domain is a part of a polypeptide chain that is independently stable or could undergo movements as a single entity with respect to the entire protein. These are found in polypeptides with more than a few hundred amino acid residues. And in those, you'll often see that they fold into two or more domains, sometimes with different functions. So how do people figure out the structures of proteins? There are two very common techniques. The first is X-ray crystallography, and in that, the protein must be purified and crystallized, and then X-rays are shined onto the crystal, and then the X-rays will diffract in a characteristic pattern whenever they hit atoms, and that data, that diffraction data, is collected, and then the structure is determined from that data. One difficulty in determining structure this way is that it can be hard to crystallize large proteins. Another method to determine protein structure is to do biomolecular NMR, nuclear magnetic resonance. And in this, you must be able to purify the protein and dissolve it, and then you collect NMR data, assign NMR signals, and calculate the structure. One of the difficulties for this is that it can be hard to dissolve the protein in a suitable solvent. So this works best with small proteins. The first oligomeric protein to have its three-dimensional structure determined was hemoglobin, shown here. And it was solved by X-ray diffraction technique by Max Perutz and John Kendrew. And for this work, they won the 1962 Nobel Prize in Chemistry. The continual maintenance of the active set of cellular proteins required under a given set of conditions is called proteostasis. It requires the coordinated function of pathways for protein synthesis and folding, the refolding of proteins that are partially unfolded, and the sequestration and degradation of proteins that have been irreversibly unfolded or are no longer needed. In cells, these networks involve hundreds of enzymes and specialized proteins. Three kinds of processes contribute to proteostasis, in some cases with multiple contributing pathways. First, proteins are synthesized on a ribosome. Second, multiple pathways contribute to protein folding, many of which involve the activity of complexes called chaperones. Chaperones, including chaperonins, also contribute to the refolding of proteins that are partially and transiently unfolded. Finally, proteins that are irreversibly unfolded are subject to sequestration and degradation by several additional pathways. Partially unfolded proteins that escape the quality control activities of the chaperones may aggregate, forming both disordered aggregates and ordered amyloid-like aggregates that contribute to disease and aging processes. However, others can be degraded into peptide fragments. A protein's function depends on its 3D structure. Loss of structural integrity with accompanying loss of activity is called denaturation, and it can be initiated by heat or cold, pH extremes, organic solvents, or other agents such as urea and guanidinium hydrochloride. Often the temperature window within which a protein will unfold is narrow, resulting in an exponential curve shown here. So here you will see that on the y-axis we have the percent unfolded, and at a particular time, denoted as the melting temperature, the protein experiences an exponential rise in the percent of it that is unfolded. We can also see an exponential curve when we look at the concentration of guanidine hydrochloride added to a protein. So here you can see that there isn't much unfolding up to 2 molar, but then as soon as we start to get to 3 molar, we see this exponential rise, and by the time we get to 4 molar, the protein's almost 100% unfolded. A famous ribonuclease refolding experiment was done by Chris Anfinsen, which won him the 1972 Chemistry Nobel Prize. Ribonuclease is a small protein that contains 8 cysteine residues linked via 4 disulfide bonds. Urea, in the presence of 2-mercaptoethanol, fully denatures ribonuclease. When urea and 2-mercaptoethanol are removed, the protein spontaneously refolds. This showed that the sequence alone determines the native conformation. This is a schematic of the refolding experiment. So here you have the ribonuclease in its native state, and here are the disulfide bridges holding all of the cysteine residues together. Then with the addition of urea and mercaptoethanol, all of those disulfide bonds are broken, which yields this unfolded protein, which was biologically inactive. But then when the urea and the mercaptoethanol were removed, the protein refolded into its catalytically active state, and the disulfide crosslinks were reformed. This schematic shows how a protein might fold. First, small regions of secondary structure are assembled and then gradually incorporated into larger structures. So over here, residues 1 through 20 form this anti-parallel beta sheet, as do residues 41 through 56, which then combine with the alpha helix here, and then they all get assembled into the final protein. Proteins fold to the lowest energy fold in the microsecond to second timescales, but how can they find the right fold so fast? It's mathematically impossible for protein folding to occur by randomly trying every conformation until the lowest energy one is found. This is known as Leventhal's paradox. If this was the case, it would take thousands of years for proteins to find their most energetically stable fold. Therefore, the search for the minimum is not random. We can think of this by looking at free energy funnel models of protein folding. As proteins fold, the conformational space that can be explored by the structure is constrained. This is modeled as a 3-dimensional thermodynamic funnel, shown here, with delta G represented by the depth of the funnel and the native structure at the bottom. That would be its lowest energy point. The funnel for a given protein can have a variety of shapes depending on the number and types of folding intermediates in the folding pathways. Any folding intermediate with significant stability and a finite lifetime would be represented as a local free energy minimum. So if we look at these different funnels, so A shows a simple but relatively wide and smooth funnel. This would represent a protein that has multiple folding pathways, but no folding intermediates that have significant stability. If we look at B, this shows a more typical protein funnel that has multiple stable intermediates leading to a final fold. C shows a protein with only one stable native structure, essentially no other folded intermediates with significant stability, and only one or very few productive folding pathways. And then funnel D shows a protein with folding intermediates of substantial stability on virtually every pathway leading to the native state, in which, for example, a particular motif or domain always folds quickly, but other parts of the protein fold more slowly and in random order. Many conditions, including type 2 diabetes, Alzheimer's disease, Huntington disease, and Parkinson's disease, are associated with a misfolding mechanism. Basically, a soluble protein that is normally secreted from the cell will be secreted in a misfolded state and converted into an insoluble extracellular amyloid fiber. These lead to disease. In summary, in this chapter we learned about important secondary structures such as alpha helices and beta sheets, how properties and function of fibrous proteins are related, how to determine 3-dimensional structures of proteins, and one of the largest unsolved puzzles in modern biochemistry, how proteins fold.